All right, go ahead.
Okay, should be working now. All right, good afternoon, everyone. Today, I want to present the Cophylab project that our planetary surface group has been working on since 2018. Cophylab stands for Comet Physics Laboratory. Today, we all have a fairly good image of what comets are, but for a very long time, mankind feared comets, seeing them as bad omens foreshadowing catastrophes. The famous Bayeux tapestry, for example, shows Halley's comet around the time when the Anglo-Saxons were defeated by the Normans. Towards the end of the 16th century, it was Tycho Brahe who first deduced from observations that comets have orbits beyond our moon. Nevertheless, the mythical image of comets persisted, like in this pamphlet from the 17th century. In 1951, Fred Whipple hypothesized that comets contain a nucleus that is like a dirty snowball. Eventually, when the technology was mature enough for a comet visit, we saw that cometary nuclei can have complex shapes. This one kind of looks like a rubber duck from certain angles. So far, 8 individual comets have been investigated by 10 different space missions. One of the most prominent comets is 1P Halley, which was investigated by a whole fleet of spacecraft over 35 years ago. Among that fleet was ESA's first cometary mission named Giotto. It approached the comet up to a distance of 600 kilometers and presented us with the first images of cometary nucleus. The new insights revolutionized our view of comets, which inspired the first large-scale laboratory campaign dedicated to cometary research. It was called COSI, which is short for Comet Simulation in German. In this campaign, the thermophysical and mechanical properties of irradiated ice-dust mixtures were analyzed in space conditions. These efforts constituted a major contribution for the planning of ESA's second and latest cometary mission, Rosetta. In particular, the development of the Philae lander would not have been possible without the knowledge gained from COSI. Launched almost 20 years after Giotto, Rosetta orbited the comet 67P Churyumov-Gerasimenko for nearly 2 years and produced unprecedented data that is still not fully understood. Delivering more questions than answers, it motivated the call for another specialized laboratory research campaign. Thus, the project Cophylab was initiated in 2018. ESA's next mission, called Comet Interceptor, is already in development and foreseen to launch in 2028. Moreover, another proposal for an M-class Comet mission is under the name Castalia Plus is in competition. For Comet Interceptor, Cophylab is already an official partner for scientific contribution. And also the Castalia proposal includes a work package for laboratory simulations, which shows the importance of laboratory campaigns. Cophylab is an international project funded by the main funding agencies of Germany, Switzerland, and Austria. It was initiated by the institutes in Braunschweig, Bern, and Graz, with major contributions from the DLR Berlin and MPS Göttingen. Furthermore, 3 other institutes from China, Sweden, and the UK participate as scientific collaborators. Before continuing with what we do in the project, here is an overview of where we stand. The biggest contribution to our current state of knowledge comes from the Rosetta mission, and hence the following points are in reference to Comet Chury. Rosetta's images have shown that comets can exhibit very complex shapes, as well as a heterogeneous surface. This aspect is particularly relevant for physical models of the nucleus-coma interaction. The data collected in Chury's coma indicates that the dust-to-ice ratio is much higher than expected. So actually, the comet is an icy dirt ball rather than a dirty snowball. The onboard atomic force microscope MIDAS, which was developed under the lead of the IWF, found that virtually all dust particles form agglomerates on some level. Even though the density of the smallest compact particles is high, the comet's bulk density is very low, which implies that the nucleus is highly porous. Due to the low albedo of the dust, it is ironically also one of the darkest objects in the solar system. The belief that comets emit gas from only a few active regions was changed when spectrometric data revealed that the majority of gas is emitted diffusely from all illuminated surfaces. While the importance of seasons on comets was known for a long time, it was underestimated as the combination of nucleus shape and spin obliquity adds to the complexity of phenomena. Therefore, it is crucial that observations cover the full diurnal cycle and seasons. Related to these aspects, there are still many open questions, of which we seek to answer the following. How do the observed properties, such as the high dust-to-ice ratio, influence the release of surface material, especially in view of its size distribution? In addition to an overall distribution of water ice mixed with dust, Rosetta also found areas with a solidified ice layer. We want to understand how exactly these layers are created and whether they are responsible for outbursts due to a local pressure buildup. Concerning the role of organic material, we are interested in their influence on the mechanical and thermophysical properties of the cometary surface. The cometary surface itself is of course also a big topic, as Rosetta observed a variety of surface features, such as cliffs, boulders, and smooth patches. If these features are created by cometary activity, understanding their relation could help deduce the evolutionary history. This also entails understanding how the volatile and refractory component were mixed before the formation of the nucleus. To address these questions, Cophylab follows a step-by-step strategy with increasing complexity. It is important to note that the main goal of the project is to understand the physics of comets rather than perfectly reproduce a cometary nucleus in the lab. In the first stage, so-called S-class experiments were performed at the individual institutes to investigate isolated parameters of simple single-component materials. This approach was specifically chosen as previous laboratory campaigns had the disadvantage that multiple parameters were simultaneously varied between individual experiments. Other activities of this stage were the construction of a large special cryogenic vacuum chamber for more advanced experiments, and ice machines for the production of microgranular ices. The design and construction of the chamber was strongly supported by IWF. During the second intermediate stage, various instruments were transferred and installed in the L chamber. After calibration and testing, preparatory experiments were performed in which multiple parameters of simple materials, as well as isolated parameters of complex materials, were analyzed. This finally led to the last stage, where long-duration experiments with complex materials are conducted in the L chamber. Here, a multitude of parameters are analyzed by a wide range of instruments. Now, I mentioned simple and complex materials, but I didn't explain what they refer to. Simple materials contain only one component, which can be refractory, organic, or volatile. The purpose is to understand how mechanical, optical, and thermophysical properties depend on the size distribution, shape, and composition of a granular or bulk medium. After characterizing the reference materials through a series of S experiments, a recipe for a cometary analog material was defined that matches as many physical properties of a real comet as possible. Thereby, chemical properties were not considered. The refractory component, which consists of charcoal and silica dust, is called Cophylab dust. It can be mixed with different volatile components in varying ratios to create a complex sample. As any other research campaign, Cophylab is also accompanied and complemented by various modeling activities. On the one hand, numerical models can be used to verify the measurements. On the other hand, they are very important for the application of the experimental results in cometary environments. Depending on the nature of the physical problem, we used various methods. To model thermophysical or gas flow properties, for example, finite element simulations were performed. The discrete element method is used to create virtual samples. These, in turn, are utilized in other simulations, such as the DSMC, which is a statistical method. Currently, we are also planning to create CT scans of several reference samples to compare their porous structure with that of the virtual samples. In the following, I would like to present a brief overview of the individual S experiments that have been performed so far. The first one is called Brazilian disk test, which is used to determine the tensile strength of brittle media. This is done by measuring the force required to break a standardized disk of compressed material, as shown in this video. The main findings of these experiments were that granular media, especially those with angular grains, have a tensile strength that is much higher than that of hierarchically packed material. Hierarchical packing means that the smallest particles form intermediate agglomerates, which themselves can pack like large particles. Cold temperatures tend to decrease the tensile strength, while for organic materials, no clear trend was found. In another experiment in Braunschweig, thermal properties such as conductivity and heat capacity were measured for different consolidated materials. Therefore, the cooling characteristic of a heat spot created by a laser was measured with an infrared camera and used as an input in 3D thermal models. Currently, the thermal conductivity of granular media is also being analyzed with heat strap measurements. Sorry, I think my PowerPoint program hung up.
Then just close it and start it again.
Yeah,
no problem. Yeah, it looks all right again.
all right, okay. This experiment was carried out in Bern with the aim to characterize the spectrophotometric properties of different refractory mixtures. This investigation played an important role for the definition of the correct ratio of silica dust and charcoal to create Cophylab dust. Furthermore, a mixture of granular water ice and estrate simulant was monitored for extended time periods to analyze the sublimation process. This technique will be used in future experiments to determine the ice content at the surface of samples. As the sublimation of volatiles is one of the most important aspects of cometary activity, there is another dedicated S experiment in Braunschweig. In this small vacuum chamber, the outgassing rate of different types of ices is measured with the help of a mass spectrometer. Here you can see images of granular water ice on the left and granular CO2 ice on the right, taken with a scanning electron microscope. While there is no particular difference of the gas production rate between solid or granular water ice, an interesting finding was made regarding water and CO2 ice mixtures. By forming an insulating layer, water ice impedes the sublimation of the more volatile CO2 ice. A different aspect, which is also related to sublimation, is the topographical evolution of cometary surfaces. As the volatile component of dust-ice mixtures sublimates due to solar irradiation, the remaining refractory component can form different types of features. The collage on the left shows mixtures of fly ash and granular water ice in different ratios, illuminated over extended periods of time. A comparison of the top row, where 66% of the sample volume was water ice, and the bottom row with only 20% water ice, gives a clear indication that the dust to ice ratio is the critical parameter that determines the evolution of surface features. Furthermore, the illumination direction also has an effect, as horizontal illumination, for example, leads to collapse events. The bottom row of the right collage shows some images collected by Rosetta for comparison. With the same measurement setup, another experiment regarding cometary activity was performed. The process analyzed here was the ejection of particles due to gas pressure from sublimation. The primary target of this investigation was to develop a method to track the ejected particles in future L experiments. After a successful implementation, the computed acceleration and velocity profiles indicated that a high-pressure environment can form directly at the sample surface, which could probably develop due to rapid gas expansion. In this video, you can see how a large chunk of dust moves as material is ejected from the surface around it. The final S experiment that I would like to present in a little bit more detail is installed in our institute here in Graz in the Comet laboratory. While understanding the sublimation process of cometary material is crucial to explain activity, it is only one part of the whole picture. Another part is to understand how the sublimated gases pass through different types of materials. That is the aim of this experiment, namely to characterize various dry materials with respect to their gas flow properties. The setup comprises a vacuum chamber that is connected to a gas supply of dry air. The chamber itself consists of two separate compartments that are connected by a cylindrical tube. In this tube, the sample is held in place by a sieve. The mathematical model that is used to evaluate the measurements is a combination of the Darcy and Knudsen flow model. It relates the pressure gradient that develops across the sample and is measured by these sensors to the gas flux passing through it. Thereby, the material-specific parameters, the viscous permeability, the parameters are the viscous permeability B and the Knudsen diffusion coefficient dk. Mu refers to the viscosity of the gas. In this figure, you can see how we perform the measurements. We increase the gas flow in multiple steps and record the steady state pressures in both compartments with multiple sensors. The main material, which was used to establish a relation between grain size and flow parameters, were glass beads of different diameters, ranging from above 4 mm to below 15 micrometers. The top figures show microscope images of glass beads with a diameter range between 355 and 250 micrometers on the left, and between 200 and 125 micrometer on the right. You can clearly see how the smaller beads are not spherical anymore due to the manufacturing process, which is an important aspect to keep in mind. Apart from glass beads, asteroid simulant, quartz sand, Martian, and lunar simulant were also analyzed. The results of this experiment are generally in agreement with other models, such as the permeability model of Cassini-Kármán. As the size of the grains gets smaller, the average pore radius also decreases, thereby increasing the resistance for the gas flow. The reason that the grains smaller than 200 micrometers deviate from this trend is related to the shape of the grains. If we look at the formula of the Cassini-Kármán model, the sphericity, a measure for the roundness of grains, enters quadratically. The equivalent sphere diameter relates to the ratio of a grain surface and volume. Even the porosity is affected by the shape of grains. As angular grains interlock more easily than smooth spherical grains, they can randomly create larger pore spaces, as could be seen on the images of the previous slide. On the left, the asteroid simulant was consolidated by putting it on a shaker table, while on the right, it was simply scooped in loosely. As a consequence, the flow parameters of such a material can vary over a large range depending on how the sample was prepared. To verify the gas flow measurements, we decided to implement the gas flow model in a finite element simulation. The approach was to use the flow parameters determined from the measurements as an input in the simulations and compare whether the resulting pressure gradients would match that of the experiment. A good agreement was found for the glass bead samples down to a diameter range of 250 micrometers. The smaller beads and all other materials, however, showed significant deviations. The most probable source for these discrepancies is the irregular grain shape, due to the reasons explained before. As the flow parameters are derived based on the pressure gradient measured across the whole sample, inhomogeneities on small scales cannot be considered. This also applies to geometrical features, such as the constriction of the gas flow due by the sieve. More specifically, it is this part highlighted in red that protrudes into the sample. Its effect was initially thought to be negligible, but simulations showed that it can significantly influence the gas flow for some samples. To mitigate this problem, we designed and created a 3D printed custom sieve for future experiments. Apart from these factors, the varying accuracy of sensors, depending on the pressure range, also plays an important role for the correct determination of the parameters. The simulations were not only used to verify the measurements, but also to analyze certain boundary effects that arise due to finite sample dimensions. An example for such an effect is that when a material is filled into a container, the grains which are directly at the wall cannot pack as tightly as in the center. The result is a slightly higher porosity in a thin layer at the sample wall interface, through which the gas can flow more easily. These images show the simulation of this effect for a sample with similar properties as the glass bead samples with the smallest beads. The bottom images show the quantities in the case of a homogeneous sample. The findings from the initial experiments and simulations will be used to improve the measurement quality for future experiments. One example I already showed, which is the redesign of the sieve. Another example would be the replacement of older pressure sensors with newer, more accurate ones. One of the challenges for future measurements is to characterize materials such as the Cophylab dust. As it is highly porous and compressible, it is very difficult to analyze without altering its structure. These images show how the sample shrinks and forms fractures when the chamber is evacuated. To mitigate this problem, we are installing a needle valve that allows us to evacuate the chamber more slowly. While working with dry granular media was crucial to establish a working measurement setup and understand the basic physical principles, we also want to take a step further in the direction of comets. Therefore, we plan to set up a larger cryogenic vacuum chamber in which the dust-ice mixtures can be analyzed at low temperatures. To ensure the comparability of our experiments with those of our partners, we also plan to install a microgranular ice machine in Graz, similar to the ones that our partners already have. From the modeling perspective, an alternative to the finite element method is the so-called direct simulation Monte Carlo, which is already being successfully applied by our colleagues in Göttingen. We are currently also using the discrete element method to generate virtual samples and analyze their porous structure. The way we do this is by first simulating the process of filling a container with spheres using the DEM software called LIGHTS. Hereby, we can also control the parameters such as the friction between the individual particles or the amount of vertical force to be applied. The output of the simulation is the position and size of each sphere. We then divide the sample into arbitrarily small sections like the rings of a tree. After having established a method to efficiently and analytically calculate the volume fractions of all spheres that intersect the cylindrical segments, we can finally compute the radial porosity distribution. This example visualizes the effect of a boundary layer of increased porosity. And now we come to the highlight of the Cophylab. The L chamber is a cryogenic vacuum chamber that was specially designed for the study of cometary analog material and the physics related with it. When fully equipped, the chamber hosts 14 types of instruments and devices that simultaneously record various parameters. One instrument that I would like to highlight is the so-called CSMD, which was designed at our institute in Graz by Günther Kagel. Here you can see it already installed in the chamber. It can be used to manipulate a sample and measure specific mechanical and thermal properties. The cooling system of the L chamber can achieve temperatures below 120 Kelvin, and a turbopump creates a vacuum of around 10⁻⁴ pascals. These conditions can be sustained over many days as the chamber was designed to simulate multiple day-night cycles. Experiments with the L chamber also require a set of peripheral devices, of which the most important one is the sample holder. To prepare a special dust-ice mixture, it is first placed inside a large glove box and then submerged into liquid nitrogen. It is filled with dust and ice that was prepared in dedicated machines. Finally, a transport car transfers the sample holder from the glove box into the chamber. After having transferred all the instruments to the L chamber, we have just recently performed our first L-class experiment in the chamber. Our colleagues in Braunschweig have created this really nice time lapse that I would like to show you. Here you can see the sample holder inside the glove box, which is being submerged into liquid nitrogen. For this experiment, we decided to start with a layer of solid water ice. The strings that you see here are thermal temperature sensors that are aligned to create a spatial temperature profile, or to measure the temperature in a spatial profile. Here, a layer of mixture of glass beads and granular water ice is added. This is another thermal sensor. In the end, a layer of pure glass beads was added. The aim of this experiment was to determine whether a layer of glass beads in this case, which could act like that layer of dust, would impede the sublimation, or how it would generally influence the sublimation of the water ice below. Then finally, with the help of the transport car, the sample container is extracted from the glove box and moved towards the L chamber. As you can see, it requires many people to perform every step of this experiment. That is also why it is a L-class experiment, which is characterized that multiple teams and experts come together in a lab to perform the experiment, as opposed to the S-class, which can be performed at the individual institutes. This white part is the cooling shield that needs to be first dismantled and slid aside so that the sample can be inserted into the chamber. Then it can be moved back, fixed again in its place. And after closing, the process of evacuation and cooling starts. Here we are testing whether the machine to lift the scale or to move the sample container away from the scale works. That construction was made so that the sample can be manipulated without pressing onto the scale. Like, as I had mentioned, the illumination can be run for multiple days or can be switched off as desired to simulate different day and night cycles. I would like to thank the whole Cophylab team and really praise how hard they have been working during the difficult times where the project had to be kept running with a lot of telecons and remote work. I would also like to draw your attention to our social medias. We have a YouTube channel and a Twitter page, of course, also the website, cophylab.space. And I would be happy to answer any questions that you have. I hope you have quite a few, then we can have a nice discussion.
Thank you very much, Sunny. So, do we have questions? Yeah, Peter, please just go ahead.
Yeah, thank you for the demonstration. My general question is, I mean, what you can learn about comets depends on the skills in making these materials, right? I mean, once you have the material, you can measure things, and then hopefully you can with some space missions, I guess, compare these samples, right? But so how would you say, how realistic are these materials you are creating? I know it's a very general question, but maybe this is kind of the key of the whole science with it, right?
Yeah, absolutely. So, of course, like you said, we can confirm or verify how good our materials are with the help of space missions, but it's exactly the data from Rosetta that we use to, for example, come up with this Cophylab dust by comparing the size distribution of the dust particles, by comparing the spectral properties, the albedo profile. That's the aspects that we focused on when we came up with the recipe for the Cophylab dust. And of course, one aspect would also be the chemical composition. But as this project is focused on the physics of the comets, we did not try to create a material that really reflects the chemical composition as well. And the experiments related to the tensile strength, for example, that investigated the tensile strength of various organic materials, because there was, well, the idea that organic materials could be sticky and increase the adhesive force of material, which would be a very relevant factor when we think about dust ejection from the surface. But the data from the experiment showed that there is no clear trend. So the tensile strength of organic materials varies over 4 magnitudes, I think, of like measured in kilopascal. So these experiments then help us to further narrow down how our sample should be, of course.
But say what have you learned? So what makes a material kind of realistic when you compare that to actual measurements in space?
The instruments from Rosetta found that the particles of the comet form agglomerates on many different levels. So like the smallest individual particles come together to form agglomerates, and these agglomerates then again can combine to form pebbles. So this hierarchical structure is really important, and we need to consider that when we create our analog materials. So if we just take simple dry dust, that won't be representative, because by forming these pebbles, the pore structure is very different than when you just have a uniform dust that has a very uniform porous structure.
What is your porosity overall when you have such a larger chunk of material made? What is the effective porosity there?
So that can range depending on how we prepare, but and it's also, of course, a different story on the Earth with the gravity working. But I think we've managed to create porosities up to between 60 and 70%.
60 and 70%.
Yeah.
And what has been measured? What would be the goal?
Around 80 or a little bit even higher.
Okay, interesting.
Yeah. So we're still not quite there. But of course, one very important aspect is that we scale all the properties to the Earth environment, because we have a much higher gravity here. So we also need to adapt the cohesive forces of the material.
Okay, thank you.
Cyril, Simon?
Yeah, Cyril, please just go ahead.
Cyril, yeah.
Yes, so I just had one question about the light source that you're using, Sonny.
Yeah.
How what type of light source is it, and can you control the type of like spectrum you can actually feed into that system or not? Can you sort of look at a precise like wavelength range, for example, UV, or what type of ranges would actually kind of affect the surface in different ways? That would be very interesting, I think.
That's a good question. Yeah. So far, we have been using a solar simulator, which is one type is with a halogen lamp, and the other one is, I'm not entirely sure, but it's also it's not a light source designed for a specific spectral analysis. So it's actually more focused on delivering the energy, really the
Right.
thermal or well total energy to the sample, rather than doing the spectral stuff. I mean, we have a spectral we have a spectrometer to analyze the reflected light, but we do not have yet a light source that could achieve that.
Okay, yeah. And do you have any idea of for example, how the EV would impact, or if it would be more important or not, or if it is more like an infrared that you need to look at? I'm not entirely sure myself, so that's why I'm asking.
Yeah, I have to admit, I'm not like expert on that part of the comet either. But since for a comet, the only light source is the sun, with the sun spectrum essentially. For the cometary activity itself, I think the thermal energy is probably more relevant than the individual spectra. But I mean, for chemical reactions, it might be relevant whether how much UV radiation and stuff you have.
Yeah, right. The reason I'm asking is because obviously with the solar cycle, you have like quite a lot of variations, especially in the EUV, or UV and EUV ranges, and that could impact also how things are going. And for example, when we were looking with Rosetta at certain variations of the irradiance, the EUV irradiance, we were wondering if this would have impacts on maybe jets, appearing on the surface, or some sort of, catastrophic outgassing at the comet, very collimated. So that's all. Maybe that's something to keep in mind more for discussions with surface people. I'm not a surface person myself, so this is just a general question. Thank you.
This is actually also thank you. This is actually a very nice idea for another future experiment, if we can get our hands on a solar on a light source that could control, where we could control the spectrum.
Yeah, super. Thanks.
Thank you.
Some more questions from anyone? Yeah, Helmut, go ahead.
Connecting to Cyril's one, my comment, I think if this is really relevant, then you should expect when the comets came in played a role in the early solar system, then you will have to deal with much more extreme UV fluxes than at present even. So would be interesting to see such effects today in some sense, and then probably if you can reproduce some observations, some bursts also connected to this today, then one could probably try to extrapolate this that happened in the early history, when you can then artificially move up with the radiation in the lab, for instance.
Yeah. No, this is really a very nice idea for future experiments. I will pass it on to the team.
Okay.
Maybe just a very general. Hans, sorry. Yeah. Okay, Hans, go ahead, please.
One question, maybe I missed it. Do you also have electrodes to measure electrical parameters?
Not in the L chamber, but we did perform measurements in the past. I think even before the Cophylab project started. Actually also during the Cophylab project, the electrical properties like conductivity or permittivity were measured in dedicated other experiments. I haven't presented it in here, but I know we did those.
Thank you.
Peter, you also have a question?
More? Okay.
Yeah, if I may ask another question.
Sure, please.
I just wanted to make you maybe aware of an interesting problem that we are having when looking at protoplanetary disk modeling, especially, in the era of ALMA, everybody is interested in millimeter opacities. And there's a particular problem, namely that if you have, say, pure silicate material, which is non-conducting, that is giving you not a very large opacity. So you can, of course, with the right size of particles, you can get a reasonable opacity, and that's what people usually assume. But there is actually another way to create rather large millimeter opacities, and that is to add some kind of conducting material. And I was very intrigued that you took graphite, because this is actually what we also do. We add in our model opacities, which we do with Mie theory and optical constants, we add amorphous carbon to it. And that has the property that if you also have some kind of irregular shapes, then you get this kind of antenna effect, so that electrons can actually start to go up and down. And this creates, I mean, this can create actually very large opacities, although, and then the particles don't need to be that big actually. So you can have large millimeter opacity even with small grains if they are a particular shape and material. And I wonder, I mean, is there any scientific justification that you take into account graphite and maybe not some other material? Because this is conducting, and that would change the millimeter opacity. So is there any insight from an analysis of cometary dust that it needs to be graphite? Was it found? Or is it just a guess to put some carbon into it?
So the main reason that we used graphite was for the albedo, to make the material darker. That is well related to the reflectance, and I guess opacity would be more like measuring the transmittance.
Yeah, it's connected, right? So if
it's connected, yes, yeah. But we approached it, I guess, from the albedo side, and didn't. I'm not sure if anyone actually considered this fact that it would increase the conductivity. But there's no, like, if there was another material that would also give the same albedo without altering the size distribution of the particles too much, we could also take that. So there is no really the argument that would speak for graphite or coal. Yeah.
Principle, you could also take iron, for example, that would have in the effect that I'm describing. That's also possible. You just need a conducting material, and then it depends also how you mix it. So the recipes you are using numerically to simulate a mixture of this, we assume it's completely mixed to microscopic level, right? And then you get a effectively conducting material, and that changes the opacity behavior. But it could be anything, and we don't know. And you can't observe it. All these materials have flat spectroscopic properties, so there's no feature also that you could observe. So we only know more or less that there is something that is there that makes it more grayish, and also especially in the, say, near infrared. Also, if you would take just silicate, that would be rather transparent. I mean, you can scatter, but it's difficult to get any absorption. And there is also the key. If you mix in a little bit of iron or so, then it's immediately dark. So we know it's dark, but we can't say what it is. And so I just wondered whether there's anything particularly known about graphite. Because for us, it's just a wild guess. Yeah, but thank you.
So anyone more? If not, I have a question on the very bigger picture. So the next mission that's interesting in cometary science is Comet Interceptor. Is that right? And what will Comet Interceptor do, like, different to Rosetta? And because I have no idea about the mission. And is it something also available to you, particularly some kind of data set that Comet Interceptor will get?
So the biggest difference to previous missions would be that the type of comets, the type of comet that is planned to be visited. I mean, so at the moment, it's not decided which comet will be visited, but Drury and Halley, they have passed around the sun several times. And that, of course, has caused the material to be ejected, have interacted, and in total have altered. And the hope is to, with Comet Interceptor, to catch comets that will have the pristine material, really unchanged since the dawn of the solar system. And of course, getting that data would be really invaluable to just get an idea of whether the material or the data of the material that was observed so far is a consequence of the activity, or if it's just how it interacts and how much it changes them.
Is there a lander on that mission?
No.
Okay.
Sorry, I'm answering for you. But the Comet Interceptor, the main, I would say that that's a very good point. The difference is the target, but the second difference is also it's a flyby mission. So you're going at 70 kilometers per second, like next to the comet. So you won't have the capabilities of following the comet like we did for Rosetta. And then of course that also means that we will have mostly remote sensing observations of the nucleus surface, and what we will get most of in situ data will be dust gathered in the instruments there. And the closest, we're thinking about the closest approach will be between 600 and 1,000 kilometers from the nucleus, and it depends of course on so many things, including activity. The target that we have is going to define all of this sort of on the spot. So we'll have this sort of taxi point where we'll stay at one of the Lagrange points for a while before trying to look for or to go for one of the targets that we have. So we hope that we will have one of those interstellar beasts coming through, but we'll see.
That would be the jackpot, right?
Yes.
So just for clarification, so the dust measurements are actually comparable then to Rosetta, like the Rosetta instrument that was developed at IWF, right? I mean, there is something like that where you can measure the dust in situ on the Comet Interceptor mission. That's also something that you can use, right? Okay.
About specific instruments, I'm not sure yet, but I suppose if the dust from the coma is to be collected, then I'm sure there will be something that will analyze it. I mean, it would be a shame to fly through a comet's coma that is really that is coming to the sun the first time and then not collect any dust particles.
Yeah. Okay. So Cyril and Peter, do you still have questions? Because I see the raised hands, or is it just
Sorry, no.
Yeah.
I can remove that.
All right.
Just to finish on Comet Interceptor, we'll have three point measurements. So we'll have a mother spacecraft and 2 probes, and that means that will also definitely have an impact on what kind of measurements we'll have. We'll have distributions of particles in both in sizes and also spatial distributions. And that's also quite a big indication of what's happening on the surface.
All right, any more questions? The hour is almost over. If not, then I think it's all right to close the meeting here. So thanks very much again, Sunny, for a very nice talk.
Thank you for
so we saw very clearly what's going on in your lab and for answering all the questions. And yeah, see you then in 2 weeks. There will be an external person from the High Energy Physics Institute who talks about machine learning, with massive data sets that they got from CERN. Just a very different viewpoint on how to use machine learning in physics. Okay, so thank you very much.
And maybe one more comment. So actually the next colloquium will also be about laboratory physics. So we have Gerhard Wurm. He will tell us about dust charging and what it might mean for evolution and in disks and life, etc. So I hope this kind of connects very well with the talk we heard today.
Great. All right. Okay. Thank you. See you, everyone.
Thank you.
and
Bye-bye.
have a good day.
Thanks, Tony. Thanks, Christian.
Thank you.
See you around. Cheers.